Okay, this is a new concept and a very important one. This is what calculus people refer to as the area problem, and it's one of the most important uses that we have for antiderivatives because the area problem, it turns out, generalizes to all kinds of useful stuff. It starts with the question, if you have a curve, and in this case they've given us y equals x, which is a plain old straight line at a 45-degree angle, they say, find the area of this region using some kind of formula. Now, I'm going to do this first using no calculus whatsoever, because there's a simple way to do that. And then I'll show you the calculus way. And at first it's going to look overcomplicated, but then I'm going to tell you that you can use it in a huge variety of situations, that it's extremely powerful, and you'll hopefully trust me about that for a little while, and then you'll see as we do more examples just how capable this new thing is. So if we wanted to attack this with no calculus at all, and we had this shape, and they said find the area under it, well, that area is a triangle, so its area is 1/2 base times height. The base distance is x. The height distance is also x, because this curve is y equals x, which means the y value of it is exactly the same as the x value, so you can use x both times. The area ends up being 1/2 base times height. So the area ends up being 1/2 x squared. Fine. All right, so that's the answer. We know it's correct because it was some simple geometry and we're good at that. Now, here's the calculus way of doing the same thing. There is a theorem, and you know it's a big deal because they call it the fundamental theorem of calculus, which says, I'll lay this out and then we'll talk about it. The area under a function equals its antiderivative. That's the short version. The area under any function equals its antiderivative. Now there's more to it. We can put specific numbers into this, and we will in a moment, but for now I just want to show you that for this curve, the function was y equals x. So if we say our function was f of x, and it just equals x, then its antiderivative, and there's a thing in calculus where if a function is lowercase f, sometimes we refer to its antiderivative as capital F. It's like small f scaled up by one step. The antiderivative of this would be, what is it again? Take the power of x, increase it by 1, multiply by the new power. That looks familiar. Calculus just gave us that same area, and it was awfully easy. So that's kind of good. And what you're going to see in future problems is, if you have a shape like a parabola or some wavy polynomial line where there is no geometric formula for the area underneath, calculus can still do them, and it does them easily just by the step of doing an antiderivative. So we're going to be able to find areas underneath anything. And if you've taken physics, you've been told that things like displacement equals the area under a velocity curve, or change in velocity equals the area under an acceleration curve. With this, we're going to be able to find the area under curves no matter how complex their shape is, pretty much, and that's going to do a lot of work for us. So the big message for this first part is that the area under a function equals its antiderivative. Now, there's more. It gets better than this. If you want something that isn't just in terms of x, maybe this triangle goes from, say, 0 to 5. I'm making up numbers now. Let's say this starts at x equals 0 and it goes up to x equals 5. The antiderivative can handle that as well if I just add a few more details. So we'll keep all of that, and I'm just going to add more into this fundamental theorem here. The area under a function equals its antiderivative, and more specifically, the area under a function from a to b where a is the left edge of the area you want to find, and b is the right edge of the function you want to find. So here I'm saying the area between 0 and 5, this area here, is equal to the antiderivative, and I'll say evaluated at b minus its antiderivative evaluated at a. The compact way of writing this is that the area under f of x from a to b equals capital F of b minus capital F of a. So this is the antiderivative with the right edge number plugged in minus the antiderivative with the left edge number plugged in. Let's see if we can actually do that up here. Again, first I'll do it without no calculus at all, and then I'll do it again with the antiderivatives, and you'll see that it works that way also. So, if this triangle is 5 wide and 5 high, then a reasonably complicated grade 7 kid who knows their area formula could tell you it's 1/2 base times height here. So it's 1/2 times base times, the height is also 5, 25 divided by 2 is 12.5 for the area. So there's our geometric way. This way says, if you want the area under that line, find its antiderivative, plug the right edge into it, which is 5, then plug the left edge into it, which is 0, and you should get that same area. So let's do that. See if it works. If it doesn't work, I'm going to be so embarrassed. So our function is simply x. Its antiderivative is power up by 1, divide by the new power. Okay, so what I have to do here is big F at 5 minus big F at 0. If you put 5 into this, you get 1/2 times 5 squared. And if you put 0 into this, you get 1/2 times 0 squared. You can see what's going to happen. It's going to work. 5 squared is 25 times 1/2 is 12.5 minus, in this case, this is 0, 12.5. Good. So, if you do an area like this, without the numbers in it. You remember when I first set this up, I didn't tell you the left or right edges. I just said find me in general what the area under would be. Then you are doing what is called an indefinite area or an indefinite integral. So if you do this without numbers for the edges, we write that as the integral of f of x dx, and that's it. This is called an indefinite integral. Indefinite integral. Indefinite as in we're not being specific about where the left and right edges are. And that means when you complete this, your answer is going to contain x's, because you haven't nailed down how wide this thing is. There should be no way you can get a fixed number for something like this, except in some weird situations. This second one, where we knew we were going from 0 to 5, is called a definite integral, because it has defined left and right edges. You write that, integral f of x dx, but this time you put the boundaries on it. If it's going from 0 to 5, you put the left boundary on the bottom, you put the right boundary on top, and now you have a definite integral. And you read this, the integral from 0 to 5 of f of x dx, or the integral of f of x from 0 and from 0 up to 5. Definite integrals, because you're plugging a number into them, your answer should come out as a number with no x's in it. So an indefinite integral, you might end up saying at the end 1/2 x squared or something like that. For a definite integral, your answer will be like 11 or 12.5 or some such thing. Now, just before I wrap up, did you notice in here that I didn't mention C's when I was doing these antiderivatives? If you did, you're absolutely right, but there's a good reason why we left them out, and here's what it is. I'll put the C's in and watch what happens when we go through this antiderivative. It's okay, it's not going to change the answer, and if you notice that, good on you. I'm glad you're catching that detail, but with integrals, especially areas, you can get away with ignoring that C, and here is why. When you do this antiderivative, you start with x, you get an antiderivative which technically should have been 1/2 x squared plus c. But now look what happens when I do this calculation. F of 5 minus f of 0, I end up getting 1/2 of 5 squared plus c. That's my antiderivative at 5 minus 1/2 of 0 squared plus c. So when you do this, you get 12.5 plus c minus 0 plus c, which is 12.5 plus c minus c. No matter what, every single time, guaranteed, I promise, these c's are going to cancel out, and they will have no effect on your finished answer. So anytime you're doing an area problem, it is okay to leave the c's off. You can put plus c and watch them cancel out if that makes you feel better, but I've watched pros do this and they don't even bother. They know these c's are going to cancel, and so they just don't even mention them. And it's understood that that's okay when you are doing an area problem.